starting now, is I want to just go over that task from last week. And I apologize for that first question. I just want to apologize for that. I remember what I did. I made the G down at the bottom 0, and then I thought, no, I'll make that one the 90, and then I changed where the 90 was, and then I forgot to put the 9 by the 0. So apologies for that, but most of you got that one. The directions were great, so I'm very happy that you know your directions. I just want to go through, there were a few very small things. So I'm just going to go through number 2 with you. So I'll read it to you. So a boy is swimming across. Can you see that? Sorry, I don't know why it's looking blue again. It's stupid. Yeah, okay, you can see it. Okay, so a boy is swimming across a river at 0,82 meters per second heading north. Okay, so if you have your Cartesian plane, right, and he heads north. Okay, you all got the north right. So that is 0,82 if you don't want to write it down. Now remember, you can indicate any vectors as arrows. So whether it's displacement, velocity, acceleration, forces, all of them can be represented with this. Now the thing is that as he was swimming across heading north, there was a current flowing down the river. Okay, now obviously if you are swimming and you are swimming in a current, it is going to take you with it a little bit. Okay, and so we had to consider the current as well. And so the current is flowing 1.5 meters due west. And I think some of you got a bit confused between your east and your west. I know I also always want to go that way, but remember west is this way. So just remember that. Okay, so west is that way, and it was, the magnitude is 1.5 meters per second. Okay, I'm not going to bother putting the units in now. Now, girls, what I want you to see here is I saw it a few times where this was the resultant. Now, just be careful. This line here, yes, we are looking at, if we do a triangle like that, and we can see another triangle, that's that angle. But when you need to do a bearing for this, that's where the problem comes in if you don't put your correct direction, if you don't put your correct resultants. Now let's think about this. If somebody is swimming in this direction and there's a current pulling him in that direction, that means that he would land up going in that direction. Okay, sorry, I'll put this in silent. Okay, does that make sense? That if something is, he's going that way, his aim is to swim across, but there's a current pulling him down, so that means he's landing up in that that resultant. So if, let's say you were in a helicopter above it and you were watching the swim and you're watching him, and relative to the sides of the bank, or the banks, the river sides, you would see him in this direction, even though he's aiming like that, because the current is pulling him down, he is going like that. Okay, does that make sense? Girls, what I want to say to you is that always, all 3 of your lines are going to start at the origin. Maybe that will help you. Okay, so all 3 of your lines are going to start at your origin. So if you're using Cartesian plane here, you would have to start all your lines at the origin. That will help, I think. Okay, then, oh, no. Sorry, I'm looking at it on my phone, so that's all. Okay, so that's what was happening here. So it said, are the magnitudes above velocities or speeds? Now, if you go back and you look and you see that I put speeds under scalar quantities and velocities under vectors. Velocity and speed, you can have the same magnitude, and they're both measured in meters per second, but velocity will always have a direction. So these had a direction, so these would be velocities. Okay, And then that was the drawing I was looking for. So I wanted to see your north, your west, and your resultants. And then lastly, calculate the magnitude. Now, girls, what you can see now is you can use your rectangle now. So only now, once you have your correct resultant, can you then do that, where you're making those dotted lines and you're making yourself a square or a rectangle. So let me just take this out here. Okay, because that is not supposed to be there. Okay, and now notice that I've only got the 2 triangles now. Now you can look at your triangles. And remember, this side here is the same as that side there because we have a rectangle and opposite sides are equal. So we know that this side here is 0.82 in magnitude, and this side here is 1.5 in magnitude. And we know that we made 90-degree triangles, so all you had to do was work out with your hypotenuse. Okay, so you had Pythagoras to do, where it was r squared is equal to x squared plus y squared. You don't have to give me the formula for Pythagoras, you can just work it out, but just don't forget to square root your answer. And then the r, what did it work out to be? I can't remember now. Because no, was it 1.7 something? Something like, I think it was 1.71 something. Does anyone remember? I'm speaking on that. Did you guys get my marking back? Did you see where I marked?
Yes, ma'am.
Did you see the ticks and stuff?
I don't know. Let me check.
Okay, because don't only look at the mark that you got. Try, I've edited, you'll see there's one, when you've handed in, you can see what you handed in, and then there's an edited version. That's where I ticked. Now, Mr. Stadler, actually, I'm amazed, but he told me about this, that I can mark on my phone, and it is so much better because I can actually tick on your work. Gemma, the girls at school, I'm getting their stuff today. I'm sorry, I couldn't make it over the weekend. My dad's coming to the school to do some repair work or fixing or something, and Mr. Stadler's going to give him that pack for me to mark, and I'll mark them as soon as I get them, okay?
Okay, ma'am, no problem.
Sorry, girls. Maybe we should look at Gemma taking photos, and then at least I can mark it at the same time. Because what I did was some grade 11s, because remember, Gemma, you gave me labels in grade 11. And what I did was I uploaded hers after I marked it, I uploaded it onto Google Classroom so she could see hers on Google Classroom as well. So it might be a good idea just for the seniors, the 10s, 11s, and 12s. Oh, you don't see the 12s. But the 10s and 11s, maybe we should just take a photo and then at least I can mark it and upload it onto Google Classroom.
Ma'am, I did send you, didn't I send you the things?
Did you see it? Did you?
Yes,
I know you
ma'am.
sent me the grade 11 one. Oh, no, please tell me you didn't. Did you?
I'm checking right now.
I've got labels.
Yes, I did send the grade.
I'm so sorry, girls. Okay, I'll do it now. I'll do it today. Okay, I'm so sorry. I don't know what. You know what? I think I was getting confused with the grade 8s that you were going to give to Mr. Stadler. Oh, so stupid. Okay, I'm sorry. I'll mark them. It goes quick. I'll mark it. Okay. Does anybody else have any questions regarding your task that you just want to clarify something? Okay, so if you go into Google Classroom, you can see where I've ticked. If you open the edited version, you should be able to see that there. If anybody does it and anybody else doesn't know how to get it done, please share it on the chat. If you can't access it, just ask on the chat and I'm sure somebody will respond. Okay, so today we are carrying on with our motion and vectors. So page 3, I want to talk to you about force diagrams and free body diagrams. Okay, so free body diagrams are the most important here. So let's just look at what a force diagram is. So there's a difference between the two. I actually started you last year with when we did grade 9 and those vectors. I started you on free body diagrams, but obviously I didn't call them that. Okay, I just called them force diagrams for you. So force diagrams are pictures showing all forces. Remember to label, put arrows, whatever. Okay, I'm not worried about the force diagrams. Force diagrams, as you can see here, says not examinable. So force diagrams are not examinable. However, free body diagrams are. Okay, and these are the most important ones. And we have actually been doing free body diagrams now. So the thing is, there is no picture. Okay, so you don't draw any picture. You have a dot that represents the object. Are you all going, oh yeah, last year we did that. Remember, we put the dot. So when they were pushing a box, the box was the dot. I hope you're remembering this. Okay, so we use a dot. Arrows represent the forces and must point away from the dot. We never point towards the dot. It is always away from the dot. So if you're getting confused and you're not sure, just always remember the tail of the arrow starts at the dot. Okay, is connected to the dot. Labels must be full names. So you say weight, or you say force A on B, or okay, normal. There's a normal force that's coming, but we'll only talk about that next year. Friction, air resistance, anything. You have to label in full words. So you can't just put, so for example, weight, the symbol for weight is FG, okay? You can't put FG as a symbol unless you put a key. Now, we'll tell you about this as we go. We'll draw more and more, and I'll just keep reminding you about the things, so don't worry. All right, so we're going to see here. So here's Larry, okay, and Larry is pushing on the box, okay. Now, if we had to look here at Larry, we could see that he's pushing over there. This is just a rough drawing, okay. We also probably realize that there's friction acting, and we know that friction always acts in the opposite direction. Okay, we know that the box will experience a force, okay, on the ground because of its weight. And there is another force that is actually pushing back up from the weight, but I'm not going to include that now, okay? I'm not going to confuse you with that. I'm only going to do the forces that you are familiar with. Okay, so if I now had to draw a free body diagram, so this would be considered a force diagram, okay? And you can do that. That's friction. That's Larry on the box. This is weight, so I can even go FG here. Okay, that's just a force diagram. So now I'm going to do a free body diagram. So a free body diagram means whichever object is experiencing the forces, that is what the dot's representing. So last year, I'm hoping this is like ringing bells here. I would say to you, let's look at the forces on the box. Let's look at the forces on this person. Let's look at the forces on, so we picked one person all the time, or one object, and then that was made your dot. Okay, so remember now, you have to always point away from the dot. So if we're going to show Larry's force, we would start and we draw an arrow representing Larry's force from the dot, and we would label force of Larry on box. Can you see, girls, it's not enough to just say applied force here, okay? You need to be specific. And this will help you later on when you do really hectic force diagrams and Newton's laws and things like that. So you need to be specific here, okay? Then, so we know it's that one force. Then we know that there's friction acting opposite to the motion. So I'm going to go like that. Now, what I'm going to do is I'm going to make it slightly smaller than this one. Now, remember, the size of the arrow still indicates a magnitude. So because I'm going to assume that he's moving, okay, so we're going to go, there's motion. Okay, so because there's motion, I'm going to assume that he has overcome the friction and his force is actually going to be bigger than the friction. Okay, so we can actually just call this friction. Okay, we don't have to say friction of box on ground. It's fine to say friction. And then the last force that is acting on the box, not acting on the box, that is the box is experiencing is its weight. Okay, so we can then say weight. And again, you don't have to say weight of box, you can actually say weight. All right, so those are the forces that the box is experiencing for now, and those are free body diagrams. So this would be considered your free body diagram. So what I want you to do is, it's not on your worksheet, but I was looking through your textbook, and what I was thinking now is on page 261, number two. Okay. It says there, I'm going to put it under here, and I'm going to adjust them a little bit just so that you can then draw free body diagrams with them. Let me just check that you can see. Oh, yes. Okay, so what it says here, it says, describe each of the following forces clearly, starting the following. Who or what exerts the force? On which object does the force act? On which direction does the force act? I don't want you to worry about that. I want to talk about this. So what I'm thinking is I'm going to adjust these slightly so that you can draw free body diagrams to practice, because in the textbook I've obviously, because remember, when you teach IEB, you don't have to follow a strict curriculum for 10, 11, and 12. You get given a curriculum, and then you can spread it over 10, 11, and 12 as you like. So majority of the time I keep to the grade 10 stuff, and then 11 and 12 we do together. But I've taken the step to do free body diagrams with you this year rather than next year. So that's why it's not in your textbook. So what I'm thinking is, let's pretend that he is actually going to kick a ball. Okay, so we can say kick a ball. Okay, and I want you to then look at the ball. Okay, balls, forces. Okay, free body diagram for the ball. The man pushing the car is fine. I want you to take note of the direction here. Okay, that's fine. The hammer striking the nail is fine. Men jumping, this is so weird. I don't know what they, so a man jumping on the earth, with the earth. So what can we do there for men jumping? No, don't worry about that one. Okay, just do 2.1, 2.2, and 2.3 right now. And then I'm just going to stop the recording. So I'm going to check, we can draw it together. So I don't want you to leave. So I want you to just draw them now, 2.1, 2.2, 2.3. And then I will go through them with you as well, okay, before the end of the period. So I'm going to give you about 10 minutes to try this. So I'll leave this on here so that if you want to take a look at this, you can then do that. Okay, so 10 minutes, start now. I want you to do free body diagrams, and I'm going to work through them with you just now. Okay, I'm just going to mute myself. Right, anybody still busy? Okay, I'm going to carry on there. All right. So let's take a look now. So the man kicking the ball with the ball's forces. So remember, you're going to have your dot representing the ball. Okay, now obviously the man's force is going to be applied in that direction. Okay, so remember, you always start at the dot, and that's going to be force of man on ball. Now, what I do want to say here as well is, remember, I want you to use your space. So you can draw this up like quite big on your page. Don't try and cram it all up in small space. If you need more paper, you can ask for more paper. So please make sure that you've got enough space to work with. What could happen as well is if the ball's rolling on the floor, it will also have friction in that direction, and it will have a weight. Okay, those are the forces that I need you to know for now. All right, then let's take a look at the man pushing the car up the hill. Now, it's very important that you get the angles right here as well. So you can see that it's up a hill, so it's at an angle. So the man is pushing in that direction. You actually show it like that. Don't show as if it's horizontal. You actually do a direction, okay, in the direction that they are moving. So this is force of man on car. Okay, what could be acting is in this direction. You can have friction. Now, this is the clincher now. Which direction would weight act? Now let's think about what weight is. Weight is a force due to gravity, and it always goes to the center of the earth. So even though you have a hill, it will always be down like that. So that is actually the direction of the weight. Always, always, always. Okay, this was a little bit of a trick question. Yeah, I wanted to see how you did. Okay, so man of car, he's going up because that's the slope of the hill, but the weight is always going to be acting vertically down. Okay, and then the last one, which I asked you to do, was the nail. So here we've got a nail, and obviously the hammer is pushing into the ground, into the wood. So we've got force of hammer on nail. Yeah. Now we also know that there's a lot of resistance here, okay, because it's going into wood. So we can show friction. Okay, and then the last one is the nail's weight, which is also acting down. So I want you to be careful when you do this. What you can do is you can make the dots a little bit bigger so that when you do this, you can show two straight vertical forces down from there. But yeah, you've got to try and make it so that it's, and you can, it would probably be shorter. I would imagine the weight of the nail was less than the force on the hammer. Otherwise, yeah, so let's swap those two. So the long one I just drew, now we can make that the force of the hammer, and this one we can make the weight. Okay, any questions regarding free body diagrams? Remember, girls, that it's not only forces. You can look at any vector. So even the one that we looked at with velocity. So if we had to see, this is the boy, and his velocity is in that direction, and the velocity of the water is in that direction, that would be his free body diagram and we know we do this with a Cartesian plane. So the Cartesian plane actually forces you to do this correctly. Okay, so that's why I like the Cartesian plane method. Any other questions? I'm actually done for today. I didn't think this was actually going to go as fast as what it did. Anything that you would like me to go through before we go?
Ma'am,
Yes.
there was an activity we did in the last chapter. I think it was Think Tank 4 in the reactions in aqueous solutions.
Yeah.
Could you please give us the memo to that?
Sure. Let's mark the thing. What can you remember the page?
Page 231.
231. Okay,
Yeah.
everybody turn to page 231. Let's mark that quickly. Let me try and find it on here so that I can give it to you. Okay, turn to. Oh, no, I've got the wrong one. Classify the following salts. Okay, so not that one. Okay, I'm going to put it under here now so you guys can mark. We'll take a look now as well. Okay. I'm just putting it back there. It's not, is it working? No, it's not. Okay, I'll. Okay, so you should see sodium chloride was yes, it was soluble. Calcium hydroxide slightly. If you put yes for that, it's fine. If you put soluble. Copper carbonate was insoluble. Silver nitrate was soluble. Ammonium sulfate was soluble. Lead bromide was insoluble. Magnesium nitrate was soluble. Lead nitrate was soluble. Silver chloride was insoluble. And zinc hydroxide was insoluble. Okay, then did you have all the rest to do as well? Did I give you the whole of Think Tank 4?
Yes, ma'am.
Okay, so the next part, they say it was describe the relationship between the temperature of the solubility and the solubility of potassium iodide. So as the temperature increases, the solubility of potassium iodide decreases. Okay, you could see that on that graph. Then the next question was describe how solubility of copper sulfate is affected by the increase of temperature. So the solubility of copper sulfate increases at an increasing rate as the temperature of the solution rises. Now, girls, if you, it's a pity I didn't go through this with you. If you take a look at that with the copper sulfate, you'll see its curve. So the rate is increasing all the time. If it was a straight line, you'd just say it's increasing constantly. But because the rates, it's increasing, but at an increasing rate, it makes, have you done functions yet? If you look at it, it's like an exponential graph. So that means that it's an increasing rate. And then the last answer there is sodium chloride. Okay, any other questions or things that I need to do with you? Now is your time to ask. Okay, well, we're going to end off a little bit early today then. It's just gone 1:45. I'm sorry. But I don't want to start the next section because I want to do it in one full lesson. Any questions?